So today we have the fourth lecture of our series Introduction to Machine Learning. We are continuing to get through the libraries that will be probably needed by you when we are dealing with all that machine learning problems. And on the previous lectures, we considered so-called NumPy library. So now we know how to do computationally efficient calculations with the Python. And today we are getting our hands on the second library, so-called Pandas. So Pandas is the library that we will use to get some information from let's say, databases. So Pandas is basically a database. This is, I would say, quite useful database. So we will be loading some CSV files. We'll be doing some manipulations with them. We'll be extracting some information from that CSV files, and everything will be done with Pandas. This is an in-memory database, so please don't expect from it too much. So I don't think we'll be able to load, I don't know, a terabyte of data in Pandas, so you'll probably need some different tools. And of course, serious machine learners use a pretty big number of different tools, but as we are just starting our way into the machine learning, I think that Pandas will suffice for all our needs, and we'll be able to process all that databases and all that examples that we will need to deal to understand how our methods work. Of course, in future, you will learn some different databases and get some more tools into your toolbox, but here is the start. Okay, so Pandas has two central objects. The first one is the series object, and the second one is the data frame object. So let's start with series object. As you might guess from its name, series contains some series of data. So that may be some sort of, I don't know, some time-dependent data or something like that. And you can perform a number of manipulations with that data. As you see now, I will be using some sort of visualizations throughout all this lecture. And once again, these visualizations are not some part of some standard library, but I'm using my own functions. So it's done for this course only. You can find, well, basically code in here in helper functions. It contains at least display pandas. And we will get pictures like this. So here is the example of created series. You see that series is indexed with numbers 0, 1 to 3. And we have information that is stored in that series. So some sort of numbers, 0.25 and so on. Okay, what else can we do? We can, for example, we can print values that are stored in series. And here you see that I print data.values, and I get a list of numbers that were stored in that series. I can print data.index and get some range index, some object that is basically indexing that series. I can extract data from the series by using some sort of slices. So here I'm using slice data 1 columns 3, and I get some slice from data. You can see on the picture what I have sliced. So I have sliced index 1 and 2, and here is the full data from 0 to 3. NumPy array has so-called implicitly defined index. So working with series is a little bit similar to what we had with NumPy arrays. And NumPy array could be indexed by a so-called implicit indexing. When we are working with Pandas, we'll get to that when we'll do something with data frame of Pandas. We will see that it has at least two types of indexing. It's the implicit and the explicit indexing, and they have there is a little bit difference between them. So here's an example of indexing Pandas series explicitly. So I create series, I give some data to the constructor, and I give some index I want to be used. So for example, I want to index my series with some sort of characters, so A, B, C, D. Here how it looks like. So it's sort of small table you see here, index and data inside. And once again, I can extract some data from there using explicit indexing. So data char from B, I get 0.5. So as you see in this row of the table. Of course, I can use some sort of implicit indexing and get some data by that implicit index. That will be still okay. Another example shows explicit indexing with numbers. That's okay as well. So I'm indexing my data with numbers 2537, and I'm able to extract some data using one of that numbers. So that's okay. Series can be used as a substitution for Python dictionary. Here's an example for you. So I have a dictionary that contains states and population, and I can create a series from this dictionary. So here is the series I have created. And I can work with this series, and I can extract data from that series the same as I could have done with Python dictionary. So here is an example. I'm asking about population of California, and I'm getting some number from that. An interesting thing I can do is getting slices. We weren't able to get some sort of slices from Python dictionary. Well, of course, you can emulate that in some way, so you can get some keys from that dictionary and just ask for values from certain keys and so on. But here is the quite a natural way to get some slice from the series. So they are ordered in some way, as you see on the table left and table on the right. That is basically the slice of the from the table on the left. I'm asking about population from Texas to Florida, and I get Texas, New York, and Florida extracted from from the table. Please note that the last object, Florida, was included. So when we are dealing with all that explicit indexing, it will include the last index that you were requesting for. If I am requesting for some slice from NumPy array, you remember that when I'm asking slice me from 1 to 10, the element with index 10 will not be extracted into your new array. Here I'm using so-called explicit indexing. It's some sort of subtle difference, but I want you to know about it just in case if that makes you some sort of bugs in your code. That here I'm asking from to slice from Texas to Florida, and Florida will be included, as you see on the right. Okay, so some more examples on series. So creating some series, indexing them different way. So I can create it just from bare data. I can create it with some sort of index, and you can see here that I'm just giving the number 5 and a large index, and it understands that I want to put number 5 as a value into each row of the series. I can series from Python dictionary. I create it with the Python dictionary and with some sort of index. As you see here, index is in some sense overloading this dictionary. So I have dictionary with keys 1 to 3. But my index wants only 3 and 2, so only 3 and 2 are extracted from that dictionary. So it orders the dictionary in the same way as your index is ordered, and it extracts only that data from the dictionary. Okay, so it was that was about series object, but what we'll be dealing with much more than just series object, that's probably data frame object. So data frame object, you can think about it as some sort of table with data. It may have a much more complicated structure than series object has. And with this object, we can perform a number of different manipulations. So as I show you examples, that's basically the object into which we will load data from our CSV files, for example, and then perform some manipulations on it. So when we are doing some sort of cleaning of data, when we are doing some sort of substitutions, removing some redundant data, and so on, that will be most probably performed on the level of Pandas data frame. And then you will get from that data frame some sort of NumPy arrays that can be used in functions for some sort of machine learning. So that will be passed to that machine learning methods that we will study in the future. So here's one more example. I have a dictionary of population in different states. I'm creating a series from it. I have dictionary of area, creating series of it, and I have states, a data frame that I am creating from these two series. So basically, I'm collecting two series into one big table. And here you can see this table in the example. So I have names of the states, I have their population, and I have their area. Please note that these two series, they were merged along their index. So you don't have like a table that contains states, population, and empty column of area, and then some sort of, once again, states, empty column of population, and then area. You have everything nicely merged into one table, and for each state, you have information on its population and on its area. From Pandas data frames, you can extract columns. Really nice functionality. You will need it here and there eventually. And it's performed using square brackets and name of the column. So note the syntax, you will probably need that. And with this sort of syntax, you can get only the information you are interested in. So if there are too much columns in your data frame, there is a lot of redundant data, you can remove it at least partly just by requesting some columns that you need and disregarding all the rest. Okay, so it has its index. You can see index. It's a separate object in Pandas. Here I can request for all columns that live in this data frame, and I get my columns. Once again, a really nice functionality because sometimes you have, I don't know, some sort of CSV file or Excel file or whatever. You load it into your Python code. And for example, you don't actually know what's going on in there. So what is this database, what data it contains, and so on. So probably your first step will be to print names of the columns so that you can get some idea of what is this everything about. So what is this database? Okay, so here is example of extracting columns. That's okay. What else do I have? Okay, so creating data frames different ways. So here is an example when we are creating a data frame from a list of objects. So here you see I have a list of dictionaries. Dictionary has some sort of key and value, and I am collecting everything and passing this list into the constructor of data frame. And I have a data frame constructed. So here you see this small table. So A and B that I have used in my dictionaries are used as the names of the columns. So these are the names of the new columns. Index is creating just from scratch. So it's just numbers 0, 1, 2. And here is basically the data. So these were the values in dictionaries that I have used when creating list that I used when creating data frame object. Here's another example. I have a list of dictionaries with, let's say, missing data. Of course, that's some sort of interesting question for you as the programmers. Why? So I have some function, so I have some constructor, and I should pass something into that function. And of course, if I'm passing some sort of list of objects, I'll be interested in what kind of objects can that be. So how free am I when choosing how to construct the objects that I put into my list? So, okay, for example, I can put their dictionaries. Good. But what about values in these dictionaries? Should they always coincide or not? Or let's say keys of that dictionaries? How compatible should they be between each other? And what happens if I do something else? And here's an example of doing something else when I'm creating a dictionary with AB keys and keys BC. I am, well, wrapping everything that into one list, and I'm pathing it to the constructor of the data frame object. And what I get at the end of the day is this table with columns A, B, C, and the places that it hadn't any information how to treat them. So for example, I had column A in my dictionary number 1, but I don't have column A in my dictionary number 2. It just puts none, not a number. And so it is possible to create some sort of tables that will contain missing data. In many cases, you will see some sort of not a number or something like that in that table. Okay. Now creating a data frame from a dictionary of serious objects. Yes.
What's with the third table? It has like strange type or structured array. Yes.
Yes, that's a table created from a NumPy structured array. I have somehow avoided this part on the previous lecture, but I guess if you are using some sort of NumPy structured arrays, that's arrays that contain, I don't know how it's to put that. Let's think, if you know C language or C++ language, you know there is something called like struct. So a structure that is basically, that contains some information that you can have different fields in there and so on. So this is a way to emulate that sort of thing. So you can take an integer, floats, strings, what else do you need, and to wrap everything into one package and to use that as an element of a NumPy array. This is called a structured array, and of course you can describe types of the fields that you have in that NumPy array. And here is an example that in case if you are dealing with that structured arrays, you can pass them into constructor of the data frame, and you will get well, some meaningful results. So you will get a data frame with all that information incorporated in there.
Okay,
So
so
yeah,
it does mean like integer with 8 bits and a float number with 8 bits. So,
yeah, that's basically that's it. So
okay,
you have
mhm. So,
Sorry.
one more question just about not numbers. So if we have series with not numbers, but for example strings, it will also feel empty, like missing strings with not numbers, with something else.
well, if you have a NumPy array, let's put it that way, you can have some sort of holes in that array. So as you remember, if I have, I don't know, array on 100 elements, I'm telling I want one-dimensional array, 100 elements. It just can't be that there is no value for element number 50 or 47. If you are using some sort of floating points, you can, of course, consciously put some not a number into there or infinity or something like that. But NumPy arrays, they don't allow missing data in its strings.
I mean in that data frames, like in second data frame, we have not a number on second. On the second, yes, it's here not a
Here,
number.
yes,
So,
yes.
but if we, for example, will have not numbers but some strings in those dictionaries, and again empty values, so will they be filled with something like empty strings, or also will be not numbers or something else?
I guess empty strings, but we
Okay.
can probably we can check that. Probably we can check that. Let's start.
While it runs, can you please in Zoom switch the audio device to the JBL?
Okay, now let's find our example. Yes, it was this one. Good. So let's try X, Y, Z. Well, no, I was wrong. It's still filled with not a number.
Okay.
Yes. No. Okay, I guess that was the answer for the question.
Yes, thanks.
Okay. How much time do we have?
Till the break?
Yes.
About 30, 40 minutes.
40 minutes. Oh, okay, very good. Okay, so here is creation from dictionary of series objects. Once again, we get columns, and each column contains information from that series object. That's good. This one from two-dimensional NumPy array. Please note keywords like columns and index. So like NumPy array gives me this area, so all the numbers I have in the table, and columns with index, they basically describe me how do I name the columns and how do I name index. So this border area is defined by these two keywords. Okay. Pandas index object. I don't actually want to get very deeply into that, but I want you to know that Pandas data frames and series, they are indexed with some sort of special type of object. It's something like, I don't know, if you've seen range in Python, you can think that in some sense, index is some sort of tricky range. Of course, you can create them. Their init function or their constructor, if you wish, is open for you, so you can use it. So here I'm creating some sort of index with numbers. You can extract something from that. You can even make slices of index. That's pretty okay. That's really good because you can get some sort of index, you can manipulate with it, and then with that manipulated index, you can extract some information from data frame object or from series object. So here is the example when I'm requesting its size, shape, number of dimensions, and type, and here I get all the information needed. Index is immutable. So when I'm trying to assign something into that index, I'll get an error. So, well, seems like pretty reasonable because I don't know how to make sense from the operation of changing index. So that may mess up the whole data frame that we have. But there are some operations that we definitely consider as meaningful on indices. For example, here are two indices, index A and index B, and I can make intersection, union, or symmetric difference of that indices. There is a really nice touch that you may want to note. Please note, I'm using binary operations like AND, OR, and who knows what the third operation?
Exclusional OR.
Yes, absolutely correct. That's XOR, so exclusional OR. Please know that they are tightly connected to the operations that we perform on sets. So I am telling about some sort of intersection, but I am performing operation AND. So I am taking only those indices that are in int A and in int B. And this is basically the intersection, intersection of the indices. Okay, so how to select data? Here is the data we have. It's that's a series. It's indexed with just some random characters, ABCD. And I can extract some, I can change some data in there. I can extract it, I can assign that data with this sort of operation. So data, and then in square brackets, index, and then assignment. Please note that I don't have E among my indices that I was creating my series from. So it was not initially in the series. And you get the same behavior that we have with Python dictionaries. So if you recall a Python dictionary, if you are assigning with some key that is not already present in the Python dictionary, it will create that key for you and assign that new information, that new value to this newly created key. So series object is performing the same way, and after I have performed operation data E equals to, let's say, 12, I have a new row in my table. So here is my new data table. Data was modified, so you might see in the code that when I'm visualizing information, I'm first visualizing my old data frame, and then I'm using my, then it, after it is modified, I'm visualizing it once again. Okay, I can extract something from my series, that's good. I can test that something is in my series, that's good as well. I can get keys in the same fashion I could have done with the Python dictionary. Here I have them. I can transform, I can get items. Python dictionaries have items as well, and you get them as some sort of pairs, key and value. And here I'm transforming that pairs into some sort of list. Here is one more example. It's slicing by explicit index, and please note that final index is included in the slice. So here's an example. I'm slicing data from A to C, and I have a result A, B, and C. But I can slice by implicit integer index. So here's the catch. If you have series or data frame object, you can get information from there, you can extract it from there by using either explicit or implicit indexing. Explicit indexing uses index that I have here in this column. Implicit indexing refers to them as some sort of array, and you get element by some sort of its, let's say, number in that array. So here is slice with implicit indexing, and it behaves much as Python as NumPy arrays. So please note, when I am slicing from A to C, I am basically getting three elements, A, B, and C, so C is included. When I am slicing from 0 to 2, slice is performed by implicit indexing, and this means I will get only element 0 and element 1. I don't get the element number 2. So this is some sort of tricky part, and sometimes you may have some problems or bugs in your programs if you don't pay attention to what kind of index are you using. Things get even more confusing if you are using, let's say, numbers for implicit and explicit indexing. There is a way to solve this problem, but I want you to pay attention to that. So it may happen that you are using numbers to index your series or your data frame explicitly, and at the same time there exists some sort of implicit indexing of your data frame and your series, and if you mess them up, you will get wrong results, so you'll be missing some elements or something like that. Okay, so masking. If you remember from previous lecture on NumPy arrays, we have pretty the same situation here. So I can do some sort of masking. I'm getting data and saying I want my data to be bigger than 0.3, lower than 0.8. And with that sort of mask, I want to extract data from my series object. I can use fancy indexing as in here, so I can get just a list of indices I want to extract and get the information out of there. So really nice functions to have. Okay, what's that? This refers to that sort of implicit and explicit indexing I was telling you about. So here is some sort of series, and I can refer to that series by using either explicit indexing. So here is the syntax. I use data, I put a dot, and I set loc. It's some sort of locator or location. And then I use explicit indexing. So here I am asking about slice 1 to 3. And here I have my results. So I get element 1 and element number and element indexed 3. So I can use data 1 or data log 1 to get, so here are examples. Or I can use implicit indexing. And here I use data.ilog. So this I tells you I have implicit indexing. And here I perform some sort of slice, and you see the result of this slice. So please note which elements have we taken out from our array. So this is element indexed by 3 and indexed by 5. Why did this happen? So I have 1, 2, 3, but I get these elements. So we can think that we have some sort of internal index that indexes this element as 0, this as 1, this as 2. When I'm slicing 1 to 3, you remember that implicit indexing, you will not get the last number, the last index you have in here. So you don't get 3, but you ask for element indexed 1 and 2. And here are the elements indexed 1 and 2. It's B and C. But this is implicit indexing, and this is explicit indexing. That will get you these two elements. So I know it's getting a little bit confusing for you, and that's pretty natural. But what I can tell you, just you should just first pay attention to this sort of things. So if you are indexing your data with some sort of numbers, I want you to know that there can be some problems if you mess up with implicit and explicit indexing. You will just get wrong data out of there. So probably I could advise you to use this sort of syntax like .ilog or .log to basically say to Pandas which kind of indexing you want to have. So you will just explicitly define your intentions. So you say, I want implicit indexing, or I want explicit indexing. I guess that will make your life a little bit easier if there is some chance of messing up with all these indexing things and get some wrong result. Okay, so data selection in data frame. Good. So we have selected some data from series. Let's do the same thing from with the data frame, and we will have the same problems with implicit and explicit indexing as we had in series. But anyway, so selection from data frame. You may note that now syntax with all that square brackets is used to extract whole columns from the data frame. You can use alternative syntax that uses not like square brackets, but dot and then the name of the column. And here is the tricky question for you. How do you think, why do we have these two types of syntaxes for basically the same thing? So you are just extracting a column of data, and you have either the ability to use square brackets and then some sort of string put into that brackets and get your information out of there, or you can put dot and the name of the column and get your information once again.
Probably in first case we are more flexible. In second, we are strictly like we can't put like variable or something. Also, it's like reminds a class somehow in second case. So, more strict.
Yeah, that reminds a class. That's a good point. As I always say, there are no absolutely good solutions and no absolutely bad solutions. So we have some pluses and minuses to both of them. How do you think? What is some sort of plus or of this syntax with a dot?
Probably strictness. Like we should always know the name of the column, its right name, and probably it better verified and like this.
So, well, a good point. It some sort of reminds you about a field of a class. That's a good point. And this syntax is not so, let's say, so wordy. So you use, it looks a bit cleaner. So maybe this syntax is more like preferable if if you don't want to write too much of characters and so on. But the left syntax, it has some other classes, and it's free of some restrictions that you probably might guess the right syntax has. For example, which sort of restrictions can you guess for the syntax on the right?
All the values are hard-coded and not obtained dynamically at runtime.
That's a good idea. So if I have some sort of variable that contains name of the column and I want to extract that column, I can definitely use the syntax on the left, but I will get some sort of troubles using syntax on the right. So that's a really good point. Okay, can you think about something else? What about the naming itself?
We
Can I
can use
call
numbers.
the column? Numbers, good. What else?
It can the name of your column can coincide with some internal name.
Well, that's not a big problem. Can I call my column, let's say, hello world?
Yeah.
Yes?
Yes.
And how do I use syntax on the right in that case?
You can.
There's some sort of problem, yeah, when using syntax on the right. So what would I write if I use that syntax with column of hello world?
You should probably use on the left syntax, right?
Yeah, I should use syntax on the left because there is some sort of problem with syntax on the right.
Yes.
If I use syntax on the right, I should write something like data dot hello world. And the problem is that there is a space in here. So you might guess that Python will not interpret that as I want because it's looks like some sort of separate instruction for it. So how should it know that this is not an instruction and this is, I don't know, some sort of name of the column? So when you are using syntax on the right, you have some sort of restriction on naming of your columns. So you can't name them as you wish. I can't name my column hello world. And this problem is basically alleviated with the using of the syntax on the left, because I can pass into that square brackets any string I want. And basically it can be hello world or something else. And this is pretty common situation because when you are creating some sort of table and you are, I don't know, you keep that table in some file and so on, you'll be pretty much willing to, let's say, equip your table with some meaningful names of the columns. So that when you load it into, I don't know, into Excel or whatever program you use, you want from the start get some idea what information are you keeping in that table. And some descriptive names will be very nice to have. And very often that names will require you to use few words. Of course, you can use some sort of naming conventions and let's say some right number of words in a camel case or so on, as we do with variables in Python and other programming languages. But in many cases, you can just get away by using this sort of syntax and not restricting yourself to naming your columns in some quite awkward way. So you just use normal words and you give them some descriptive names that will be helpful when you are dealing with the tables and when you are analyzing that information. So that will be good. Okay. So here are some sort of more examples. Here is an example of using internal method. Yeah, it was a good point to remember about that internal methods. if you call for some reason your column pop, you will get in conflict with internal method pop of the data frame. Quite rare situation, I should say. It's much more common to have all that spaces problem and so on, but well, you can get into that troubles as well. Okay, so what else? Adding new columns may be performed, at least in some cases, quite easy with the data frames. For example, you have already constructed a data frame that contains information on area and population of certain American states. And now you want to have some sort of population density to, I don't know, to get some idea which states are more densely populated. Why not? And you can perform them just using quite simple operations. So I write data density equals data pop divided by data area. And that's all. So that will create for me a new column. It will find out that there is no density column in my table. It will create a new one for me, and it will assign information obtained by dividing element-wise, the same way as we did with NumPy arrays. When we were performing some operations, we were getting element-wise result. And it will put it into that column. So here is the result as you see. Transposition operation. I'm just trying to put my table, let's say, on a side. It's rotated 90 degrees, if you wish. So the things that were columns in my table, they become rows, and my rows become columns. Well, why not?
So there are
Really,
new indices like area, pop, and density.
Yes. So absolutely correct. So here are your new index, area, pop, and density, and here are your new columns that you can extract. I guess it's rarely used in practice, and because most cases you will have very large tables in terms of index, but not so many columns. And I don't actually have any idea why would you want to put that on some sort on site, because if you just want to extract some sort of row from the table, you can do that. It's not a big problem. But anyway, okay, so here is the method to extract values in form of NumPy array. Really nice operation. So if you have some sort of database and you have features in that database, you will, well, most probably you will think about all these tables because we are doing machine learning at the end of the day. And you will think about columns like some sort of features, so some sort of measurable characteristics, different. And your rows will be your measurements. So each row will be basically your data point. So extracting information this way will be very convenient for you because most functions that we will use from sklearn, they will want to get information in this format. So like NumPy array, two-dimensional that contains your data points, and each data point has a number of dimensions, and each dimension is basically some sort of feature. Okay, here I'm just doing something with that array. Okay, what else? Here is some sort of explicit and implicit indexing. Basically, everything I told you about series is valid in this case, so I'm not getting into that. So basically the same thing. Okay. Here I'm using some fancy indexing and masking. Once again, you probably remember, or I hope that you remember from lecture number 3, we had quite similar situation with NumPy arrays. We could mix up different forms of indexing when referring to one array. Of course, I mean that this is a multi-dimensional array, and we had to stick to one form, let's say form of indexing for each of the axes. But different axes could have different forms of indexing. So for example, I could just fix some sort of element along one axis and say I want just elements with number 0 in this axis. And we could use, I don't know, some masking along other axes. So something should be true along that axis, and along some third axis, we could use some fancy indexing and so on and so on. And here is basically the same example, but just for data frames that use different sorts of indexing along different axes. A tricky question for you. I have here syntax like data.lock. What type of indexing is this?
Explicit.
Yes, absolutely correct. And what should I have to write to make this implicit indexing?
ilock.
Yes, absolutely correct. So ilock will make this implicit indexing. Okay, what else? Some sort of modification of data with explicit and implicit indexing. You see that right here. So I had old information, and here I have some sort of new information. Here's 146 that I was assigning, and here is 15,000 that I was assigning. So you can modify your data frames if you wish. You can change data in there. Okay. While indexing refers to columns, slicing and masking refers to rows. A little bit maybe confusing part of the syntax with data frames, but basically that's the way it is. It has some internal logic to it, actually. So yes, it may be confusing. So when I am getting when I was working with NumPy arrays, I could get one element from that array just by setting its index, or I can make a slice and get some sort of range of elements. Here, when I am trying to get with the same syntax, I have got one element from NumPy array, I will get one column from data frame. And with the same syntax, I took slices on NumPy arrays. I will get a range of rows from my data frame in Pandas. And some sort of philosophical, let's say, question for you. How do you think why it's done this way? Well, all these things were created by humans, and probably they were thinking something when writing all that this way. What do you do with the same way? What was the idea behind this? I don't think it was to confuse you, yeah. So probably they don't want to confuse their users, but for some reason they think, well, let's do it this way. So let's take syntax for indexing one element, so indexing, to refer to the whole column. And when we are doing some sort of slicing, let's refer to rows. Why not referring just to rows everywhere, or just to columns, or whatever?
I just like I didn't understand when we indexing we also could like get rows, or I didn't understand while using.
No. If I take, I don't know. So here is my data. Hopefully code still runs. Okay, is it live or not? Yes, it's still, or it's not that data. No, it's not that data. Okay, let me find where I have created data. Data. Yeah, I guess it's this one. Okay, let's return in here. Let's check. Okay, that's good. Now please note, I ask about area. You see, area is a column. That's the whole column of the initial data. Okay, let me print data once more here, that you see the table. This is the table data. A really nice feature we have right now in Google Colab. It's this sort of representing tables. When I was just starting this course, there was no such instrument. So in most cases, you will see these visualizations that I have created. But maybe right now I can even not use them. I don't know, but let's leave it the way it is. So when I ask about area, I'm using, once again, square brackets. I'm passing something into there, and I have the whole column as the result. You see, this is area column. Yeah, so this is what I get. But if I'll try to use some sort of slicing, I will slice basically rows. So I'm slicing from Florida to Illinois. So please note, Florida and Illinois, it's indices. It's not columns. But when we were dealing with NumPy arrays, both slices and indexes, they were referring to pretty the same thing.
Probably indexing, like when we're receiving columns, is more useful for us in most cases when we, but I don't know.
Yes, it's really, as I told you, it's some sort of philosophical question because it has more to do with which operations we are performing more often. And of course, we want to have some more simple syntax for the operations that we perform more and more often. That's quite a reasonable idea. And it really seems like more often used to extract one column of your data and do something with that column than extract some sort of range of columns. So it may be a little bit even strange because in most cases we don't think about columns as some sort of ordered elements. So they contain very different information, and the nature of that information may be very different. And in most cases, we don't think about them like some sort of sorted and having some order. On the other hand, your rows, in many cases, they are really thought as some sort of sorted data. So for example, you are getting some time series, so you are measuring something and your clock ticks and you have some natural ordering in that data. Or I don't know, you are measuring with some device and you, I don't know, change some voltage in that device or whatever you do. And you have a series of results with that voltage increasing, let's say. So you can, in many cases, you can think about your rows of your table as having some sort of natural ordering that is inherent to the data you have in that table. But it's not the way that we think in most cases about columns. So once again, for example, let's think that I'm measuring with some sort of physical device and I'm getting some readings of data, I don't know, some current, some magnetic field, whatever I have. and I am increasing voltage, and I'm collecting that data in in a table in Pandas data frame. So you can perfectly think about the rows of this data as sorted because you were increasing your voltage and you have some natural ordering in there. But you probably can't tell me what should go first, current or magnetic field, or I don't know, some intensity of something, or some number of detected particles, or what are you doing with that device? So probably your columns will be most cases not ordered, and there is no meaningful, it's not meaningful to get some slices in them. If you just want some columns, you will most probably you will just define them by hands. I want this one, and that one. Okay. Operating on data frames. So here are a few operations that we have in Pandas. Once again, a really nice thing about them. They are so-called universal functions. And you can remember that sort of thing from NumPy arrays. Well, I should tell you that Pandas is basically built on top of NumPy arrays. It uses NumPy arrays. It will sometimes return you information in form of NumPy array and so on. So it shouldn't be a surprise for you that having some feature in NumPy array transforms somehow into a feature in Pandas. So it's really natural situation, let's say, this way. So here are examples of few functions like addition, subtraction, and so on. You can perfectly expect them to be there. Why not? Here is an example of usage of that function. So I'm using a series, and I'm basically using NumPy to perform exponentiation of data in that series. Please note that index is preserved. So I have performed e to the power of 4 on the first row, but I haven't performed e to the power of 0. So index just leaves some sort aside of the data. We are just performing operation on data. Here's an example with data frame. So I'm doing some sort of computation on the data frame, multiplying by pi, dividing by 4, taking some sign, and so on and so forth. So here are the results. Of course, it's floating point operations. So in some cases, you have really small value, like 10 to the minus 16. That's where you should have number 8. Please note, number 8 divided by 4, it's 2, and multiplied by pi, it's 2 pi. So what would you expect from sine of 2 pi? Well, basically, to be 0, yes?
Yes, 0.
Yeah. But we have some sort of numeric computation errors. And when dealing with all that computational stuff, it's really good to always keep in mind that you will always have some sort of computational errors. So here is an example when you have 10 to minus 16, but well, so please be prepared. That's the reason why basically you don't want ever to compare your floating point number with, for example, 0. So it's really okay when you do that with some integers and so on. But when we are dealing with floating point numbers, that may be a really bad situation, because you might get this sort of results. They are very small, but not 0, and you will have your if statements working not the way you expect them to work. So keep attention to that. Okay, one more, let's say, tricky question for you. So we have all these universal functions here. Do you remember from the previous lectures why I was so, let's say, excited to present these sort of functions to you on NumPy arrays? So why do we like them so much?
They were very fast. They were very fast.
Yes, they are very.
They are built with a name to be applied to the whole array at once, and we won't need to make some nested for loops to iterate through the whole array and apply it manually to every element. We can just write array and function.
Yes, absolutely correct. So it's basically the idea behind all these universal functions, and why do we like them so much is that they are implemented there in binaries, and everything is performed down there in binaries. We just pass data and get the results. No loops in Python, and as we remember, loops in Python are like, it's long to wait until they finish. We have measured the time on the previous lectures, so you probably remember that there's a really big difference. So something like 200 times, or I guess, yeah, we had some results like 200 or something like that. So it's really, really fast. So that's good. Okay, what else do I have for you? Index alignment. Good. So I have area, I have series with area, series with population. I create data frame. Yes. So I am creating a data frame, and I'm representing it right here. And here is the point that missing data is handled correctly. So indices are correctly merged. So please note that the series for area, they contain Alaska, Texas, and California, while series for population contain Texas, contain California, but do not contain Alaska, and contain New York. Here I am performing some sort of universal function on them. And as you see, this function is not performed just some sort of randomly or whatever. It pays attention to the index you have. So when I'm trying to divide population by area, it will look at the both series, and it will perform this operation in the places it can basically perform these operations. So we have California in both series. We can perform this sort of division, and we create California in our new data frame with basically result of this division. We have Texas in both series. We perform operation on Texas, we put that into our new frame. And that's basically convention that when we are performing this operation, we have some indices we can't perform this operation on. So I can't perform division for Alaska because I don't have any information on the population of Alaska. Well, quite interesting. Does anyone live there in that sort of condition? Probably some people do, yeah. Okay. So I don't have any information on population of Alaska. On the other hand, I have information on population of New York, but I don't have information on area. And these two rows will be added to our result table, but they will be marked with not a number. That will signify that either something went wrong during performing of the operation, so it wasn't able to complete. In this case, the reason behind this was basically some missing data. Okay, what else? Here are some sort of manipulation with indices. So at least one index has value, so I'm doing some sort of union on indices, doing some sort of intersection of indices, and so on. So this should hint you that if I want this operation to be performed in a certain way, so for example, I don't want to deal with the rows, I don't have some sort of complete data in all these series and so on, I can manipulate with indices and do a sort of decision. So for example, I'm taking the intersection of the indices and I'm performing operation on this intersection. or you can do some different logical operations on them that are equivalent to set theoretic operations and get your new index that you want to work with. Here's an example of adding two series. Once again, we have some sort of missing data. And we want to treat that missing data in a certain way. So for example, here I'm just performing addition, A plus B, and whatever I have missing data, I get, once again, I get none. So that's okay. I have here a function ADD, so addition of A and B. At the first glance, having two syntaxes like plus and some sort of function ADD seems redundant. But you might guess why do we may want to have this sort of duplication of syntaxes in some cases, not even in Pandas, but when you are creating your own system or thinking about designing your own classes and so on. Why you may want to have this sort of situation, so have two different syntaxes for basically the same operation.
To add more parameters, probably.
Yes, absolutely right. In one syntax, when we are using just binary plus, there is no place to add some more parameters. This is a really nice way to write some sort of addition or whatever you want if it's some sort of custom operation that you have. It's conscious, it doesn't take many symbols to type and so on and so forth. But you don't have the luxury of adding some more and more parameters. And it may happen that you want to change something in that function, and you may want to add some parameters to it. And here is like real life example that I just don't want just to perform addition. I want to add some more instructions to that addition. In this case, instruction what to do if I don't have enough data. So if I don't have enough data, I don't want just to put some not number in there. I want to put some sort of value, some filling value, in this case 0, to fill my table. Well, and here is the result of that addition. So I am adding A plus B, I'm getting some sort of not number. Here I'm using fill value. Fill value 0, what does it mean? I have for 0 index, I have value for A, it's 2. But I don't have 0 index for B. And it will be substituted with this fill value 0, and I will get result like 2 plus 0 equals basically 2. And the same situation for this row. Okay. Okay, do we have some more time?
Yes, this is the perfect time for the break.
Okay, okay, so we just this sort of table, well, does the same thing. So fill value, fill, and it fills some missing values. You can check that, and I guess it's now time to make some small break. And after, I guess, how much, 5-10 minutes? 10 minutes, we'll be back and continue with all this Pandas stuff. Okay, so let's continue. Few more examples, like universal functions between data frames and series perfectly work the way you expect them to work. So data frame, I am something subtracting, and so on. Once again, we have some sort of additional parameters for this subtract, and you may see parameters like axis and so on. So nothing fancy here. nothing really really complicated. Now, just one thing to notice, that you may have broadcasting. You may have broadcasting when performing operations on Pandas data frame, the same way you had that broadcasting when dealing with NumPy arrays. Okay, handling missing data. This is one point I want to make today. So, well, suppose you are creating some sort of database, and it may be that some data is missing. So you still want to work with your table, but there are certain cells in your table that you cannot fill in with some meaningful information. And what can you do in this case when you are creating your system? So how would you handle those cells that do not have any meaningful information? Probably, I guess I'll tell you that right away, that there are at least two approaches that may come to your mind. So the first approach is keeping together with your table some sort of mask that will keep track of those cells that do not contain any meaningful data. So you are keeping a table, you have some sort of mask, and I don't know, some true and false in this mask signify to you which data you can use and which data is some sort of garbage just in memory. And the second approach is using so-called sentinel values. This is approach when you are dedicating some exact value to signify to you that this cell does not contain meaningful information. So that's the second approach. Pandas well chose to use sentinels for missing data if Python already has some sort of new values for that data type. So for example, for floating point, you will have not a number value, none, or you can have none, the Python object. So here are some sort of examples of that sentinel values. You can, of course, check if you are having some sort of missing data in some cell with operations is null, not null, and so on. You can filter your data basing on the fact if you have some missing data in that row or column, or if you don't have. You can fill that values with some, I don't know, predefined values that you have. So for example, you don't want to have all that nonce in your table and can fill them, for example, with zeros or something like that. Before we get to syntax, I want to once again like give you some sort of philosophical question. So if you are creating some sort of database, what kind of approaches can you think for handling all that missing data? And regarding at least that two approaches I told you, like sentinel value or masking, what are the pluses or minuses of these approaches? So let's think you are some sort of engineer that creates some brand new database, some Pandas plus. How would you handle that?
So to compare, like dropping all not number, all invalid rows, or filling them with some value. Yes.
No, it's not like dropping them, but for example, suppose that you are keeping some data in memory. And so how it looks like, the data in memory. So you are creating some sort of table in memory. So let me draw that, yeah?
Yep.
So you are having some sort of some sort of table, you know that you will have, I don't know, 10 rows or something like that, and you will have like 3 columns. I'm doing some random table. And now I'm getting some information from the outside. So I'm getting some information and I'm filling this table. And I know I have some number here, some here number, and so on and so on. So I have some numbers in this table. But when I get to this cell, I don't have any meaningful number. But I can't just throw away this cell from the table. Why? How do you think why?
It's continuous. Continuous memory is
Yes,
faster.
It should be continuous, first of all. And the second thing, you are keeping track of your columns and your indices. So you are indexing this table. So you say, for example, this is, I don't know, A, B, C, D, E, F, and so on. And here are columns like, I don't know, C1, C2, C3, C4. And you should somehow signify in your system that the cell, like, what's that, D, say, comma, C3, does not have any meaningful value. It is still somewhere in the memory, so because you want to store your data like without any breaks and so on, so continuous storage, but you want to signify somehow for the user that if he tries to retrieve data from this cell, he won't get any meaningful result.
Maybe just add one byte value, like 1 or 0. Is it valid or not?
Yes, that's the approach that I called masking at the beginning. Okay, so you are you're going with masking. What are some sort of pluses and minuses of masking?
Maybe it's very precise and no, like it will always tell you and no, like you always know that there weren't values, there were not correct values. I don't know.
Okay, what's the alternative approach anyone can like propose? So one approach is nice, it's masking, so we can keep track of missing values just by some sort of keeping, I don't know, one byte or 1 bit mask somewhere that will tell us in this cell we have meaningful value, in that cell we don't have meaningful value. Okay, what else?
Maybe some kind of sparse tables, I don't know, but
okay, let's go this way. I gave you at least 2 approaches, yeah? So one was masking, the other one was so-called sentinel values, yeah?
What does sentinel value mean? It's like some kind of default value?
It's some sort of value that signifies you that you don't have a value.
Oh,
so think about not a number in floating point.
Okay, so I think it's could be the disadvantage probably of sentinel value is that so sometimes we can't define it. For example, if we have, as you say, a range of numbers and they could be like negative and positive, we just can't specify some kind of a number which will be wrong for them.
Yes, that's a really good point. So not every data type has some sort of natural sentinel value. So when we are thinking about floating point number, it's great. We have not a number there, we have something like that. But when we are thinking about, let's say, integer numbers, we don't have some sort of natural sentinel value. So any integer number is in some sense meaningful. So we can't have that in there. So yes, a big minus of Sentinel values is the fact that we don't always have some natural way to define them. That's a good point. So it's a big minus of Sentinel values compared to masking, because if we do some masking, we keep track of each cell. That's we don't basically care what types are we keeping in all that cells. We just put like true or false. Is that a meaningful value or it's not? So that's okay. On the other hand, masking has its minuses compared to Sentinel values. And maybe the first big minus is the fact that you should always keep some additional table that will define you for each cell. Is it correct or not?
We
course,
could
that's
define
used.
we could define, for example, a list of wrong indices. I don't know. It probably will
Yes,
store
you
less
can.
memory.
Good. So that's one more approach, and this approach will have some sort of, yes, it has its pluses. So now you have a list of indices that are wrong, and they define cells in a table. Good way to start, but it has big minuses. Can you spot them? So what problems would you have with this sort of approach?
We should check this list each time we check in the table, probably.
Yes, we should check that list each time we are checking the table. And even if you use some sort of special data structures that allow you to quickly check whether some value is in that list or not, that will still cost you some time. Moreover, if your your table is or some bigger part of your table is invalid and it contains some bad values, you will have quite a big structure with all that information. And on each request to your table, you should get through that structure and check whether it is there or not. Even for really nicely organized structures, your search will be at least logarithmical log n. Yeah, so probably you can't find your value more quickly in that structure. And that's why if I had, I don't know, some request to some cell, if I know its address and I can just get value from there, so it's 01, instead I get O log n. So that's a significant, can be a significant degradation of speed. So this approach has its minuses as well. Okay, so about Pandas. So Pandas tries to go with Sentinel values. It spares some memory on that separate table that we will need to have, and of course it spares some time or that we maybe I don't know, that we lose when using some different structures better organized in memory, but of course it costs us some computational time that we don't want. So that's the way. Okay, of course, if we have all that sort of Sentinel values, and we know which data in the table is meaningful, which is not, we can perform some operations with that data. For example, we can remove some rows that are not complete. We can remove some columns. We can change that values to something meaningful and so on. Here are a few examples, like I have a data frame with data missing. I do drop NA and it drops me, for example, rows that were not complete. This is a nice operation to have because if you will perform any machine learning and you will get some data, load it in form of tables and so on, then pass it to sklearn methods. you will probably want that your data is complete, because all that methods that you can just get in trouble when you are passing non-valid data into there. So something is minimized there, some functions are performed, and you are passing like none. Of course, as a result, you can expect to get none as well. So probably you want to clean your data before you pass it to any of the machine learning methods. Here is drop NA with access equals columns. So you may want, in some cases, drop away columns. In machine learning, that will correspond to the case that, for example, you have some sort of feature that is not measured for each of your rows. And considering your table, you are thinking that maybe you don't need that feature so much. So probably you can go the way like removing part of your rows, but you don't want to lose your data points, and you are thinking, well, maybe I will better lose this feature, but I will keep my data points. So that's the case that you may want to use this drop NA on access columns. Okay, so some more examples of dropping different style. So how to drop them, and so on. So you may drop columns if they, for example, contain only, not a number, the same way you can do with rows, or you can drop them when they contain some critical number of undefined values. So maybe in some cases that will be useful for you. I don't know, like you're writing some time series and you want it to be more or less complete. For example, you want at least 80% of your measurements to result in some sort of meaningful information, not a number or some infinities or whatever. You can try to fill that missing data with something. That's the thing I called in our first lecture, I call that data imputation. So of course, you are getting data from real world and you can't expect it to be perfect. And in many cases, you will load your tables and see that there are some information is missing from there. And it's your choice what to do with that information. Of course, I showed you that you may just throw away some data points or some features if you decide, but you can try, of course, to fill it with some numbers that you consider to be, let's say, relevant or reasonable for that case. And here are the methods of filling with previous value, filling with next value, and just filling with some predefined value, whatever you choose. Some more methods of filling that's works pretty the same way. Okay, here is a more, let's say, advanced part, so maybe I'll do that either quite quickly without some sort of details. It's called multiply indexed. I should have here both frames and series. The idea is the following. We can have not only the simple index I have already showed you, but we can say we can have some sort of hierarchical indexing. So like you have some index, you are indexing some sort of big chunks, then each of that big chunks you are sub-indexing, and so on and so forth. Of course, at the end of the day, your index should get to individual elements, and each row should be indexed with its separate index. Of course, they all should be different, but you can have some sort of tree of those indexing. It may be helpful in some cases. Here is one of the examples how to do that, let's say, the bad way, and how to do that the good way. For example, you have data on, let's say, population of 3 states like California, New York, and Texas. And you have them for years 2000 and 2010. you want to keep track of all that stuff in like some sort of series or data frame or whatever you want. What would you do with that? Of course, you can combine the name of the state and the year into some sort of tuple and use that tuples to index your series. So here's an example. You are just using these tuples. That seems pretty okay, unless you are trying to get some, let's say, specific information based on the part of that index. So for example, I have this table, so maybe I have it for many states or many countries and many years and so on and so forth. And for some reason, for whatever reason, I'm interested in, let's say, population for the year 2010. And what should I do to get that information from here? I will need to basically iterate through the whole table, take index, crack it open, take apart that state, take apart the year, and then compare that year with my predefined constant or with some conditions I have on that year, or and so on, and then collect it everything back again and get my data from the table. It's definitely not convenient. It was much more convenient for me if I could just define to Pandas, I want year 2010, and it will just drop me that rows of the table that are somehow connected to that year 2010. That would be much more convenient. What do I do in this case? I create so-called multi-index. So here is the way it's created. You see the hierarchical structure of this index. Here I have states, and these states are further branched into years, 2000, 2010, and so on. And only then I have my data on the population. And it's really easy now to filter whatever I want. So here is basically the syntax I have. So I just take population. I tell that the first part of the index, I don't care. So whatever state it is, I don't care. But my second part of the index should be 2010. So I am just filtering everything that corresponds to the year 2010. And here the result I get. Well, there are many things you can do with that sort of multi-indexing. For the series, you can transform them into frames and basically transform 2D multi-index into, let's say, rows and columns. So here is an example. You transform that into a table. You can do some different things, so that's pretty okay. It's a bit of, let's say, advanced stuff, so I'm not really getting into it. I want you just to know that there is such thing as a multi-index. Maybe in some cases, when you do some operations on your Pandas tables, you will get these multi-indices. So don't be afraid of them. It's perfectly okay. It's a nice thing. It's easy to work with. And you basically can work with these tables as we worked with just simply indexed tables. So once again, I can do some sort of division. I can add some columns, remove some columns. So everything is great. Okay. So here is some sort of slicing of multi-indices. Once again, I'm not getting really into that. So you see the same problems we had with some sort of implicit indexing, we all have in here. It's really works the same way. Here is an example of multi-indexing and even multi-columns. So you see that I have here some sort of patients like Bob, Guido, and Sue. and I have heart rate and temperature measured, and we have table with all these results for different years and different visits to general practitioners, and of course we can extract some data with quite simple syntax and so on. So it's okay. You can rearrange multi-indices. Well, of course, you might feel that this order of columns, so what to think like the first column when we start this multi-index and what to think about as the second column, they are in some sense interchangeable. So why not start with 1, 2 and then subdivide them into ABC? Why do I start with ABC and I subdivide them in 1, 2? And you can change them places if you wish. There is such possibility. Okay. Data aggregation, that's okay. And here is the part I really want to show you because it has to do with some sort of thinking with pandas and solving like problems with pandas. You already might guess that we can get through the whole lecture notes today. It's really too large and contains too much of the information. But actually, you don't need all that information because most cases you will just refer to some sort of documentation on pandas, and you can check all these syntax problems, and so on. You can check there, and it's not so hard to find. But some things are a little bit more tricky that I want you to know about, and I want you to think about them because they have to do something with some sort of engineering stuff. And one of the interesting concepts is like making one table from few tables, so collecting them together. Collecting few tables together is a little bit more tricky than you might think if you have never done that before. So maybe you have some experience, I don't know, with SQL or whatever, so you probably know something about that. But if not, it may be a bit interesting thing for you to think, why do we have all these problems and how do we solve them? So, okay, some simple simple function concat that concatenates me a few series. That's simple. Data frames. I am concatenating two data frames. Please note that pandas sees names of the columns and sees indices and concatenates everything correctly. So everything is concatenated correctly. Of course, you can use append function that performs appending. That's okay. What else? I can concatenate along defined axis. That was pretty expected, so that's okay as well. Now, what happens if I have let's say indices that coincide, and I am trying to concatenate. You see the result that indices are duplicated, and that's a bit no good. So when doing concatenation of tables, you should add some more parameters. So, for example, to drop that index and recreate some new or something like that, because you might have duplication of your indices, and that will impair your ability to find some information in that table. You can't use this index anymore. But whatever happens, you always can use implicit indexing. So that's a neat part to that indexing. So when your explicit indexing is for some reason is broken, you can still access your data through implicit indexing. So that's a thing to remember. Okay, here is an example what to do in the case of coinciding indices. One way is ignoring index. So you just say ignore index true, and you get a brand new index. Or you can use multi-indexing. And here I have old indices as some sort of subdivision of a new level of indexing. And this new level of indexing, I define names for it, or I define what I will write here by the keyword keys. So I'm adding, I'm transforming my simple index into a multi-index. So here is the case you may face all this multi-indexing stuff, and you can use it basically to avoid problems with indices if you don't want to drop them for some reason. I don't know, maybe they contain some meaningful information. Okay, what else? Some sort of additional parameters like sorting and so on. And here is the part I was so waiting for, this parameter join. A small parameter that changes basically everything. Okay, let me find the image for you. Yes, here it is. Okay, so here is the case. We have some sort of tables, and we want to merge those tables. So I want to get information from table 1, table 2, and I want to combine it together. Despite some problems with indices, so let's forget about it, we can have some different problems based on the fact that one table may contain columns that do not appear in the other table. And one table may contain indices that do not appear in the other table. And we want these tables to be merged. So I don't know, like I have a few separate tables with some employees, their salaries, I don't know, some vacations they were on, and so on and so forth. And I want to get that all into one big table. So I want each row to correspond to one employee, and I want all the information on that employee to be in that one table. That's pretty okay, but it may be the problem that when I am trying to like merge those tables, I get something like on the right-hand side. So I have some columns in table number 1. I want to add to them some columns from table number 2. But the problem is that not all indices coincide. So I have some employees in table 1 that do not appear in table 2. And I have some employees in table 2 that do not appear in table 1. This is the situation that when we do not have enough information to fill each cell of our newly created table. And we should do something with that. Probably you can now think of a few strategies that you might have when merging all the tables. So starting from, I don't know, removing some rows that are incomplete, or filling some missing values, and so on and so forth. So I guess you already have that in your mind. But the problem is that depending on that tables and on the data in that tables, you may use different strategies in different cases. So that's why when merging tables, you have a parameter that basically defines your strategy of merging that tables. And there are few strategies that I want you to be aware of. the same strategies you probably have seen if you ever studied, I don't know, some SQL or I don't know, any language that is connected to working with some databases. So whenever you do something with databases, you will probably see some of these problems, and you will probably have some instruments and tools to handle them. Okay, so let's get into it. Inner join. Probably you have heard that if you studied SQL. We have the same thing for Pandas, so you can just set some sort of parameter. I don't know, it's somewhere join equals inner or something like that. Here it is. How? It's not join, it's how. How equals inner. When you are doing Pandas merge and you give 2 data frames to that function. So you have 2 data frames, you say, I want it to be merged with inner strategy. What is the inner strategy? Probably in books for SQL, you see this diagram is on the right, so Euler-Venn diagram. Actually, I want to warn you, I don't like this sort of diagrams because they are, in some sense, they are wrong. They are misleading for you, and I will show you the case when it happens just in a moment. So if you already read some books on SQL, you have seen this diagram on the right. You should know that these diagrams they are misleading. Why? What it basically shows to you is what happens to the index of the table. So just to the index. So when I am performing inner join, I'm just taking those indices that coincide in both tables. So at this point, it's pretty okay. If they coincide, it means that in each table, I have complete set of columns that correspond to that index. Much more, I like the diagram I draw for you on the left. So here you see indices C and D, they coincide in both tables. They both are complete. So here I'm trying to merge tables, as you see on this upper diagram. So I had table 1, table 2. I'm trying to merge them. C and D coincide, and I'm taking them with all their columns. So at the end of the day, I get some smaller table, but it has all the columns that were present in table number 1 and table number 2. That's pretty okay. Here is syntax to perform that, so but I guess you can check that. And here is the case that shows you how misleading are all those diagrams in books for SQL. This is the so-called left join. So once again, I have some sort of strategy to merge that tables. And on the right-hand side, you see that standard picture, that Euler-Venn diagram, that shows you that you are basically taking everything on the left. And here is why it's so misleading. This thing actually corresponds to index only. So this means I will take all the indices that are present in my left table, so in table number 1. But if you look at this diagram, what is confusing? When you see it, I just took everything on the left. And you might think, why do I even have this strategy? Why do I don't just take table on the left and that's all? Why do I need some other table? And this picture on the left should be some sort of way to unconfuse you, to show you why do we need that other table. Because we are dealing not just with indices, but with data in that tables. So this means that I take the whole table number 1, and whenever I can, I add columns from table number 2. Whenever I cannot, I fill them with some sort of sentinel values or whatever I do to signify that there is no meaningful data that I can put into there. So this picture is, I guess, much better because it represents you what happens to the data in the tables. So you are adding some data to the table on the left. You are not just taking table on the left, you are adding something. You are adding new columns that you take from the table on the right. Okay, here is example of the syntax. Well, that's okay. One more join. Once again, you saw that probably in some books on SQL, outer join. It's when you take everything you can. So that's union of indices. So all the indices present were taken. And whenever you can, you take some meaningful information for columns. Whenever you cannot, once again, you fill with some sort of dummy variables, I don't know, some nulls, some nones, whatever. So here is the case. Okay. Here are some sort of, let's say, using some sort of cases when you have columns that have the same name, because of course it's a bit of a problem if you are trying to merge two tables and you have columns with the same name and you are merging them in a way that these columns should live some sort of side by side. And here's the method to untangle that columns by adding some suffixes like L and R, so I control them by hands in this case, and I'm telling when I had some sort of name and rank, and I'm merging it with the other table that contains names and ranks. I will get rank L and rank R from these tables, well, just because it was left and right. If you don't do that, Pandas will do that for you, but you lose control on the suffixes and you will probably need to draw your table or to guess somehow what kind of suffix it's added. In this case, X and Y. Maybe if we'll add the next suffix would be Z. I don't know. And one more thing to show you, one more, let's say, half philosophical thing I want you to be to know is aggregation and grouping. It's some sort of strategy of working with data that you will probably employ more or less often when you deal with some big tables and some large arrays of data. So first of all, in Pandas, we have some sort of aggregation. So we had some aggregational functions in NumPy when we were asking about some minimal, maximal elements, some mean values, and so on. The same thing we have in Pandas. That's pretty simple. So you can have a series and you can take some sum, some mean values, so on. You can do the same thing with data frames. Of course, you can define which column you want to use and so on and so forth. That's okay. But what I want you to show is this sort of strategy. It's called split, apply, and combine. This is a very useful strategy to have because it helps you to work with large arrays of data, and it allows you to perform some sort, well, not in Pandas, but if you deal, I don't know, with some Spark, maybe some different tools, more advanced, you may want to run a number of processes in parallel to make your like work with data, to make all the data processing a bit more quicker. In some cases, you may even want to delegate some processing to different servers. So you will have a number of machines, and you will delegate each part of data to that machine. So what's this strategy all about? So you have some sort of input data. First of all, you split that data into chunks. How do you do that splitting? Basically depends on the problem you are solving. So you have some sort of problem, and it is very, very beneficial for you to find some way to split your data into groups such that each group can be processed separately. So that's a really good way to work with data. Then after splitting, you apply some sort of operations on that data, you perform some calculations, and then you combine them all together. Let's, I don't know, maybe I can find some sort of example for you. I don't know, it looks all too complicated. Now let's think this way. So I have a table, and suppose I have their data on some sort of, I don't know, some planets of our solar system, maybe some exoplanets from different systems, and so on and so forth. So I have many data. And for whatever reason, I want to know some, I don't know, mean size of the planet in some system. And if you have a really large array of data, it will be really long to get through each data point and calculate all that mean values. But what can you do? So first of all, you can group your planets depending on the solar system they belong to. So you group them. Then for each group, you perform calculation of that mean value. And you can put that pool of data even to different servers. They can calculate that mean value for you, perform like all the processing of that information, and then they can give you back the result, and you will aggregate results into your final table. Well, maybe not so good example, but if you find some case when your grouping gives you some large amount of data, you have some large groups, it becomes really, really meaningful because you are like splitting your terabyte size database into chunks for example, few gigabytes, and then you deliver that data sets to, for example, different servers. They calculate something really, really complicated, and then they return the result for you, and you aggregate all the results together. So I don't know, maybe you have some very large number of photos, and you want to recognize some objects on that photos, and you may want first like split your photos into some chunks, and you send the chunks to different servers, and each server performs, I don't know, recognition of some objects on that photos. It takes a long time, then they get your data back, and you combine that data into one big table. So it's a really nice way to think about data processing. So I really want you to, I don't know, think for a few moments about it and to employ this sort of processing when you are doing some some problems that involve large data sets and large tables. Yeah, here is an example of how do we do that for some data set of planets. So Pandas contains method group by. You are giving some key to that method, and it groups your table into parts basing on the value of that column that you passed. So I have a data set of planets, and I am saying, well, group me that planets by, let's say, method they were discovered with. So there are a few different methods like astrometry, eclipse timing variation, and micro landing, and so on and so forth. And you are grouping planets by that method. It does not return you any sort of data frames or whatever. It returns you some special object you can work with. Here is an example. I'm doing like something with that object, so I have grouped them, and I can get some part from that object. That's okay. And here is example of doing calculation on that. So I have a large data set of planets. I have some information regarding each planet. I'm grouping them by method the planet was discovered with, so different methods. Then on each of these groups, I apply operation of getting median. I want to find some median of the orbital period of the planet, of some planets discovered by certain method. And then I combine everything together and display them. Okay, so here is the final table you have. So here are methods, and here are some median periods. It may not look like very meaningful to you, but for example, if you are trying to get some insights into that method, you can create table with some mean value for a period or for mass of the planet and so on and so forth. And you can make some conclusions like, oh, this method works only on very heavy planets, for example. So you have a really big mass for them. Or this method works very well on some very small planets and so on. Okay, so I guess this is the last example I'm showing to you. So probably I will just, I don't know, maybe draw one picture for you, because I think it's really important for you to have that sort of understanding of that method. We are having a table that contains a column method, and you have all these things here like astrometry, landing, so on, some landing, so on and so forth. And here are basically planets that were discovered. So here is some, I don't know, some planet 1 and so on and so forth, 2, 3, 4, 5. So what I am basically doing, I am grouping them together based on the method. So this one was discovered by Lansing, this one, for example, this one, so on. So I am separating them into one part. So I say, here is my, let's say, landing part. And here is my table with all that planets that have landing in the column of method. Then I have astrometry. Okay, here is my astrometry part. Once again, I have table, I have some planets in here and some planets in here and so on. So that's what I have. Each of these tables can be really enormous. Then on each of these tables, I perform some sort of operation. So I'm doing something with them. I'm performing some operation on each of these tables, and then I'm combining them together. So I'm doing some sort of, well, some function f on the table. I'm getting something new, some function f, and so on. And then I am combining all these tables. I'm combining them together, so to get a new table. So once again, I return back like landing. I return back astrometry. And in here, I put the result of that processing. So this is a really crucial thing because a really good way to work with data and to process data is this way, to split them, to apply some sort of operation and then combine them. That allows you to perform that operation on different servers and so on and so forth. Okay, I guess it's everything I wanted to tell you today. Some different examples you may check in our workbooks and here in our lecture notes. It's basically some sort of reference of operations you can do in Pandas, so nothing fancy, nothing very complicated. If you have any questions or statements, please.
Just one question. Are those data frames in Pandas, are we creating new data frames when performing some operations on them, or it's more like or for Pandas saving some memory somehow for us?
I guess most cases, interesting part that operations in Pandas return a new frame for you.
Okay.
Yeah, you will probably need to check some sort of documentation, but I guess that most cases they return new frames and you will need to write like new frame equals and then whatever you do. That will be the case. Probably there is some parameter like do operation in place. It can be performed in place, but these samples, I guess almost everywhere I used like something new equals some operation.
Okay, understood.
Okay, so no more questions, statements, then thank you for your attention and we'll meet, I guess, next Friday.